What is Graph AI? Graph AI is a branch of mathematics that studies graphs, which are mathematical structures used to model pairwise relations between objects. A graph in this context is made up of points and lines. For example, if you have a set of cities and you want to study the connections between them based on direct flights, you could represent each city as a point and each direct flight as a line. This would create a graph that represents the network of direct flights between cities. Graph AI is a branch of artificial intelligence that uses graph theory to analyze and interpret complex structured data. This is particularly useful in fields where data is not only large, but also interconnected, such as social networks, biological networks, and the World Wide Web. In the field of medicine, Graph AI has shown significant promise. It uses graphed neural networks to process diverse data holistically, viewing modalities as nodes interconnected by their relationships. This approach allows for the capture of intricate relationships within structured clinical data sets, such as patient records and imaging data. One of the key advantages of graphed AI in medicine is its ability to facilitate model transfer across clinical tasks. This means that models can generalize across patient populations without the need for additional parameters or extensive retraining. However, the use of Graph AI is not without its challenges. One of the main issues is the need for human-centered design and model interpretability in clinical decision-making. Since Graph AI models capture information through localized neural transformations defined on graph relationships, they can be difficult to interpret. To address this, knowledge graphs are used to enhance interpretability by aligning model-driven insights with medical knowledge. In the field of cybersecurity, Graph AI is used to generate attack graphs. These are AI models designed to assess security threats within networks. The models consist of encoders and decoders, trained using reinforcement learning algorithms. After training, the effectiveness of the models is confirmed by observing changes in loss and reward values. The generated attack graphs are then compared with those created through conventional methods to assess their accuracy and efficiency.